How am I supposed to beat a video game without being able to make my own computer inside the game? Naturally, this is the first question that I asked myself when I saw that we can build things in the new Legend of Zelda. I'm sure that the developers of Tears of the Kingdom intended for us to use this ability to stick things together to make vehicles and bridges and things that will generally help us in the game, but for the sake of science, let's build a calculator instead. Making computers within games is nothing unheard of. People have been making very impressive programs in Minecraft, for example, for years. If a system allows us to make a certain set of logic gates, then we can combine those to do just about anything that any other computer can do. We say that a system like this is Turing complete. This isn't really the formal definition of Turing completeness. We would also need infinite memory, for example, but in the way we often use it, and in the way I'll be using it in this video, Turing complete means that given enough time and possibly expanding the size of the game, Tears of the Kingdom can theoretically run any program that any other computer can, including any game for the Nintendo Switch, and therefore Tears of the Kingdom itself. The conclusion of this video is, sort of. Tears of the Kingdom is sort of Turing complete. As we'll see, there are a lot of difficulties. To demonstrate it though, I was able to put together an extremely simple calculator that can add two numbers. My regular viewers might think that this video is a little out of character. I make math and physics videos, so if this is your first time watching this channel, I'm warning you that most of this video will be explaining the math and engineering of digital logic. If you want to skip ahead to the final creation, you're absolutely welcome to. A signal in a digital computer can have one of two values, 1 or 0, true or false, 3.3 volts or 0 volts. In our number system, you can combine and manipulate numbers using operators like addition, multiplication, subtraction, division, but in a system with only two possible values, sometimes called Boolean algebra, the operators you use are things like and, or, not. So a device we call an AND gate would take in two variables and it would spit out the number 1 only if both of the inputs are 1. Similarly, an OR gate outputs 1 if A or B is 1, and a NOT gate just gives you the opposite of the input. By combining these in different ways with different variables, you can make any set of outputs for the inputs. For example, say you want something to happen only if A equals 1 or B equals 1, but not both. This is called an exclusive or XOR gate. This means that your output should be A or B, and not A and B, because it's the same as an OR gate unless both A and B are true. We can use similar logic to come up with other gates, namely NOR, NAND, and exclusive NOR. If we make some kind of device that turns two values into one following these rules, and we can make AND, OR, and NOT gates, then we've already solved our problem. We have Turing completeness. In a computer, the signals are high or low voltages and the gates are made out of transistors, but that's not necessary. The signal could be whether or not a ball falls, and we could make mechanical devices that only allow a ball to fall if two balls fall into it. Once we have the other gates, that would still be a Turing complete system. We understand how we can use logic gates to manipulate Boolean variables, but it might not be clear how computers handle data like numbers, or words, or pixel colors on a screen. To give you an idea of how this works, let's talk about binary numbers. We have a base 10 number system, so after 9, we run out of symbols and we restart at 10, 1, 0. Binary is a base 2 number system, so after 1, we run out of symbols, and we restart at 1, 0. Then after 1, 1, we run out again, so we go to 3 digits, starting at 1, 0, 0. If we keep doing this, we can represent any whole number with enough 1s and 0s. In normal math, when we add two numbers with many digits, we do it by adding each pair of digits. Then if it's bigger than 10, we carry the 1 and add it to the next digits. That's first grade math. But we can do the exact same thing in binary. The nice thing is that since each digit is either a 1 or a 0, we really only have a few options for what the sum is. 0 plus 0 equals 0, 1 plus 1 equals 1, 0 plus 1 equals 1, and 1 plus 1 equals 1, 0. If you look at just the first digit of the output, you can see that it's really just an AND gate. Similarly, the second digit is an exclusive OR gate. So with only two logic gates, we have a circuit that calculates the sum of two one-digit or one-bit numbers. This is called a half adder. It's not a full adder because once we get to the higher digits, we need to also handle the case where we carry the 1. We can do this by connecting two half adders together and then putting it through an OR gate. If we want to add bigger numbers with more digits, then we just connect another full adder. Each digit we add multiplies the highest possible number by 2, so a 4-bit adder will be able to calculate the sum of two numbers that are each under 16. An 8-bit adder can handle numbers up to 255. Here I have a 4-bit adder made with some electronics. Each of these chips has 4 logic gates inside of it, so I've connected them together to make the circuit I showed you before. We use these 4 switches to input one binary number, then the next 4 to input the other, and these LEDs light up with the sum of the two numbers. This will be my goal. I want to make this same circuit entirely within Tears of the Kingdom. I'll admit, its functionality is a little bit less impressive when you consider that adding two numbers up to 15 is on the same math level as a kindergartner, but really it's about the principle, right? Once you add memory and a clock and a display and input, making a computer is really just a matter of combining billions and billions of logic gates just like this. So let's make a computer. Idea number 1, electricity. We make paths of conducting material that trigger springs with metal items attached that either open or close new paths. Great idea, but you could only do the conducting electricity with the dropped weapon stuff in Breath of the Wild. You can't do that anymore in Tears of the Kingdom. Also, Zonai devices like the spring can only be triggered by hitting them with weapons or an arrow, not by electricity. Idea number 2, time bombs. Time bombs can trigger other bombs and other Zonai devices, so they might be promising, but unfortunately they destroy everything in their path. Idea number 3, hydrants. These make a continuous stream of water that does have mass and interacts with other physics in the game, so we can make things like water wheels and levers that get pressed when hit with water. If we place the hydrant so that the water produces the right torque, we can make it so that one hydrant turns another one on or off. It's great in theory, but making the physics work is nearly impossible. Everything has to be perfectly balanced, so I struggled to make a single gate, let alone a computer. At this point, my greatest fear was realized. Somebody else successfully made logic gates in this game while I was working on this video. I knew that that was a possibility the whole time, right? The game has been out for a month and 10 million people are playing it, so I worked frantically to get this video done, but I guess I wasn't fast enough. C7Fab on YouTube was able to make logic gates by blocking paths of light with levers, but because light can't trigger Zonai devices like the stabilizers that block other lights, the gates can't be connected together into circuits. They were able to find a workaround for this to create a 1-bit full adder. It basically uses a beam of light from a mirror for every combination of numbers to add, then blocks the beams depending what series of switches you trigger. It's a clever idea, but you still can't add onto it. Circuits can't connect, so I think the problem is still open. Maybe I'm too caught up on AND or NOT gates, and we need to consider other ways of making a computer. Take, for example, the 1965 mechanical computer Digicomp 2, and also Turing Tumble, the educational kit inspired by it. These work by rolling balls that can flip a switch that controls the next ball's direction. Each lever basically acts as one bit of memory. It's a lot easier to make an adder circuit with this system than it is with pure logic gates. We just arrange the levers like this, then we enter our first binary number with 1s to the right and 0s to the left, then we enter our second number by placing balls everywhere that there's a 1. This requires no power, only gravity, and we can probably make it with the game's materials. It took some experimenting, but after a few attempts I came up with this, a 1-bit adder. We flip these switches to enter our first number, then we drop melons to enter our second number. Let's try it out. And now, ladies and gentlemen, the most complicated calculation to ever be performed on a computer built in Tears of the Kingdom. 1 + 1. It's kind of embarrassing that this is all I have to show for all my work. I tried expanding it to 2 bits, so the hardest calculation we can do is 3 + 3. Let's see if it works. Okay, maybe not. Even if this did work, it's actually exactly the maximum amount of items that you can have fused together at one time, so until someone figures out something far more clever than this, 3 + 3 will be the most complicated thing that a computer in Zelda can do. Although my results are underwhelming, I have very high hopes for the future. I know for a fact that somebody watching this is going to come up with something way more clever than I can imagine, and I fully expect to see more advanced computers as this game gets older. Even though I can't imagine it now, I have zero doubt that somebody will make Zelda within Zelda at some point. Until then though, this has been absolute torture for me. Most of my videos are in part excuses for me to learn or do something new, and I thought that this would be an excuse for me to play Tears of the Kingdom, but it turns out that making these melons roll correctly is not fun, it is tedious. I intend on playing the game now that this video is done. Thank you to all the generous and wonderful people that support me on Patreon. If you like free math and science content and you want to support me, head over to patreon.com/physicsforthebirds. Thanks for watching, and I hope you were able to learn something.